Hi, everyone. Yeah, this is kind of a weird day, I guess. Thank you, everyone, for coming. I know it's hard. I know that it's a mess today, so thank you. My name is Avishai. I'm here to talk about Cloud Native, the pets, the kettle, and Germs. If you don't know me, then I work for Aleph. Aleph is a venture capital fund here in Israel. We invest in Israeli startups and startups that are related to Israel with the hopes of growing big companies out of Israel that make meaningful change for the community. And I personally have been in this field for many years. I started my career working on physical servers. We adopted the cloud about, I think, when was it? About 2009, 8, something like that, a long time ago. And I've spent most of my career, as most of you have, on the cloud. And I've kind of went through this transformation from using pet servers, and switching to kettle and all of that stuff. But now we're seeing something very, very different. So I want to talk about Cloud Native a little bit, because this is a Cloud Native conference. And the first thing that you do when you go to a Cloud Native conference, or any conference whose name is kind of weird, is you try to understand what the hell it means, right? So what is Cloud Native? So I looked it up in Wikipedia, the source of human knowledge, and this is what they had. Native cloud application refers to a type of computer software that natively utilizes service and infrastructure provided by cloud computing providers. I don't know about you, but I have no idea what this means. Like, absolutely no idea. Okay. I mean, either this is completely obvious and I'm just dumb, or this is, something that actually no one knows what it means. This could either be so trivial that no one bothers to explain it, or completely obscure. So I dig deeper, and I found the Cloud Native Foundation, and they actually have a definition of what Cloud Native is. Unfortunately, when I started reading this wasn't very helpful. Scalable applications in modern dynamic environments such as public, private, and hybrid clouds. Again, I have no idea what this means. But later, down around the middle of the document, I found something that was much more helpful. Containers, service meshes, microservices, immutable infrastructure, and declarative APIs exemplify this approach. Okay, which approach? What does it mean? These techniques enable loosely coupled systems that are resilient, manageable, and observable. Okay, now we've got something. We've got some principles that, presumably, if you build something that's loosely coupled and resilient and manageable and observable, then it's Cloud Native, I guess. So, around the cloud. You would notice that manageable is something that has been promised by every technology in the last 30 or 40 years. I'm just saying. But the rest, some stuff like loosely coupled, resilience, observable, that's new. I mean, no one talked about observable for a very long time. We used to talk about monitoring. Now we're talking about observability, which is slightly different, I guess. So yeah, those are new patterns, and probably they defined what Cloud Native is. But we still need to understand what they are and how we got them. So let's talk about how we started this journey, how we started our journey into infrastructure and IT a long time ago. Enter the age of pets. The age of pets is the way we used to manage servers, let's say 20 or 30 years ago. And this is my dog, by the way. She's very cute. And the reason we call them pets is we used to have servers that we tended to individually. And each one of those servers had a name, and when it broke, we took good care of it. We SSH'd into it. Maybe we installed it. Maybe we fixed whatever software problem it had. We sometimes replaced some of the hardware. Let's say that the server, maybe the disk died. We went in there. We replaced the disk. It's the same server. We just patched it. Everything was fine. So this is typical architecture of a system, let's say from the 90s or the beginning of the early 2000s. And you had a bunch of servers, and the servers had code. It was running, they were running code. Each one of the servers had a name. They were connected through a physical network, a router, switches. Of course, you had a firewall to protect your internal network from the rest of the world, which is the internet. You were connected to the internet back then. And you had a monolithic database, physical usually, to store all the data that you were using. And this was very typical. And this was a system that was manageable, it was very manageable, through tight coupling. everything was tightly coupled. It was connected by hardware. When there was a failure, we knew about it immediately. Tight coupling means that the connections are so strong that whatever phenomena moves almost simultaneously. Everything happens, very short time frames, which is good on one hand because you can probably predict what is going to happen. You can analyze it very easily. And because everything was tightly coupled, we could manage it very easily. It was very easy to understand what's going on. It wasn't very complicated. And the reason it worked, because the downside of tight coupling is that also problems travel very fast. So the reason it worked is because all the connections were highly reliable. If you remember the systems back then, we used to have enterprise-grade hardware. We used to have highly reliable storage. We bought special disks. We bought special storage devices. We bought switches from Cisco that were highly reliable and very expensive. And this is how the system survived, by a small number of highly reliable parts. And part of this reliability was achieved by having a stable environment. We couldn't cope with changes that were too fast. So what we did is we introduced changes very gradually. Maybe we did a config change once every half a year or once every quarter. We didn't update the system that much. The system was pretty stable and pretty static. And the way we imposed it, the way that we made sure that the system stayed in that single configuration that was good, known to be good, is that we had tight control over everything. We knew exactly what was the configuration of every switch, every storage device, every server. And it worked for a while. But then eventually we started going to the cloud. And when I say we started going to the cloud, I don't mean that we immediately switched to the cloud. No, this took a long time. First we had virtual machines, VMware, Xen, if you remember those days, QEMU, that kind of stuff. So at first it wasn't a big transformation. We moved the servers. It was still Linux servers, pretty much configured the same way. They still had names. We just moved them to virtual machines to consolidate on hardware. It was usually even the same hardware. So not much has changed. The database actually mostly stayed physical. Not a lot of people were putting databases on virtual devices, on virtual machines, but still, you could do it. But the application servers and a lot of the switches and a lot of those other devices were actually virtual at that point. But the architecture mostly stayed the same. And the way we manage stuff mostly stayed the same. But something fundamental has changed. We lost control of the environment. Once we moved to virtual machines, the network was no longer reliable because it was shared. So if more than one neighbor was using the same device, the same physical hardware, or maybe the same server or the same network, suddenly you got the problem of noisy neighbors. And maybe the performance was a little bit flaky, and sometimes the servers just went away. And if you were using the early cloud, let's say EC2 around the 2008 or 2009, sometimes servers just, they went into the void and you had no idea why. This actually happened a lot of times. So when we moved our systems into the cloud, into virtual machines, we started dealing with this problem of having an environment that we couldn't control. And if you remember, we needed a stable environment to get reliability so we can get tight coupling so the system will be manageable. Because we no longer had control of the environment, everything broke. So we had to adapt. And what we did is redundancy. We started running, instead of one server for everything, we run 3 or 5 or 10 servers of each type. And at this point, stuff started to change in the way that we manage our servers. For example, the names of the servers started to change. It was no longer application server. Now it had a name and a number. It was app3, or maybe service 58, or whatever. Because we had a number of servers for each type. And of course, the database had to go through the same transformation. We no longer had one monolithic server that could survive anything. We now had a cluster of servers, of database servers, usually a master and a slave with some form of failover, but you get the idea. But other than that, not a lot of things have changed, or has they? Because now when you have a group of servers, you need to start worrying about something you didn't need to worry about before. Are they configured the same way? Are they identical? Do they behave in the same way? So we had new problems in the cloud. First of all, the number of servers could change because, even if you didn't use auto-scaling, then maybe one of the servers died and it was automatically replaced or not. So you could have 4, 5, 6 servers. You didn't know exactly how many servers you're going to have at each time. Of course, the IP addresses would change because they were dynamically allocated. So you couldn't use static IP addresses in your configuration files anymore. And if the IP addresses change, that means that the network topology constantly changes, which might result in data conflicts. If you have a master and a slave, and the slave can become the master at any point, or one of the other servers could erroneously talk to the slave, then you might have data conflicts. This is now a distributed system with all the problems that a distributed system might bring. So, yeah, we had to deal with that as well. What did we do? We turned into something completely different. Enter the age of cattle. Now, what do I mean by the age of cattle? When you have a fleet of servers, you no longer treat them like pets. You don't. When you have a pet, when you had those monolithic servers, if something happened to them, you took really good care of that server. When you have 1,000 servers, you can't possibly take care of every one of them. There's no way to fix the configuration of every one of them, definitely not manually. So what do you do instead when you have a sick server? You shoot it in the head, and you get a new one. Same way that we do with cattle. I know it's a little hard to hear, but yeah, this is what we do. So we started dealing with our infrastructure in a radically different way. And at this point, something else happened. We started using microservices. We understood that if our infrastructure is something that is dynamic, it's actually easier to deploy new software, and it's actually easier to deal with failures if you split your software into multiple parts. So we no longer had a single cluster of application server. We now had multiple clusters of application servers. So we added new devices, new servers that were running different parts of code. But again, it looked kind of the same, except that now instead of application server 23, we had a number of clusters like AppyMuppy and AppyDuppy and stuff like that. And microservices, those are very interesting. So the idea of microservices is that you have a service that has a single purpose and is semi-autonomous. It can function by itself. It doesn't need other parts. And it's closely coupled to other services. And those services work as a cohort to provide a bigger service. But you could actually use each one of those microservices almost independently. And from the perspective of other services, each microservice is a black box. You're not supposed to know what's going on inside of that black box, which allows other teams to develop it independently without hindering your development plan and so on. And those services, they coordinate by having a stable API, and this is generally the idea of how it works. And it was a really, really good idea, and it had no problems whatsoever, right? So this is a diagram of what's known as the Microservices Deathstar. This is from Amazon, sorry, this is from Netflix, if I remember correctly. And this details how all the microservices communicate with one another. As you can see, this is a fairly understandable diagram, right? No, it's horribly complex. So this is what we got when we started using microservices. So for example, at Wix, at this point they have around 1,000 microservices, which is quite a lot. It's not like this yet, but it's already so complicated to understand that no one actually knows who's using what service. This is a really, really big problem. Going back to the infrastructure, what happened to the infrastructure at that point? So we started having more and more servers, and at some point, something significant happened as well. The storage started moving to the cloud. So we stopped storing stuff on disks, and we started storing them in S3 and DynamoDB and stuff like that. So that was interesting. But then we started using external services as well. Anyone using Twilio, for example? No? Anyone using Square? Yeah, a few people. PayPal? Yeah, you get the point. We started using a lot of external services, and we got to the situation where some of the services were microservices that we wrote, but some of them were external. And the boundaries between inside the cloud and outside the cloud started, going away. But okay. One of the interesting stuff that this change brought, is that we no longer cared about the internal network that much, because we were talking to a lot of external services as well. That's fine. Notice the name change? We no longer call the servers app whatever, because a lot of the times we were running containers on a bunch of servers, and you didn't even know exactly what server the container would run on. You didn't know where your service would be, and actually you didn't care either. So this is kind of a summary of the transformation that we went through. We started from having monolithic servers that had names, and we tended to them very carefully, and we fixed each one of them. And then we moved to clusters of a single service, a single monolithic service, that maybe had a name, but also had a number, because it was a bunch of the same stuff. And then we moved to microservices, where we had lots of clusters of different servers, and each one of those clusters had a number of machines. And we ended up with generic machines that didn't even have a name or a number. Now this is very interesting. If you have an ID in the server name, conceptually, when you look at this, how many servers do you have? Because if you look at app 3, you can pretty much deduce that you have at least 3 servers of that type. If you look at I82A, 4F, 21A, how many servers do you have in the cluster? No one knows. And this is because we no longer enumerate servers. We don't know, and often we don't care how many servers we have. They're just replaceable parts we don't really care about. This brought something very interesting. When you have a lot of servers, and a lot of those servers keep changing all the time. Maybe we push config changes to them, we deploy stuff to them, some of the servers go away, some of the servers come back. This happens all the time. You get an environment that's highly unstable, that dynamically changes all the time. For example, at Wix, this is statistics from 2 years ago. Production changed every 3 minutes on average. And Amazon published a statistic where that something is deployed to the cloud every 7 seconds. So you're talking about the production environment that is never stable, never, at no point in time. Which raises the question, when you're talking about production environment, what production environment are we talking about? Which production environment? Do we even have one production environment? So, no, we don't. Because, for example, every client talks to a different has a different path through the system, talks to multiple different systems. Even from a web page, you could have a number of AJAX calls, or a number of synchronous calls to different services on your microservice cohort. Some of those services might be on different clouds. They might even be from different vendors. Often today you see stuff like Intercom, which is a service that people put on their website to allow chatting to support agents. This is a completely different vendor from the original website it resides in. So they might be on different data centers, they might be on different clouds even. Some of your microservices might be talking to another microservice in a different data center for maybe redundancy, or maybe the service in that region is not active. And if you're talking about A/B tests, when you have A/B tests, for example, at Wix, at any given time, you had about 250 active experiments. And a client would have a configuration of, a very specific vector of 250 coordinates of which experiment it's currently on. So you had 250 square possible options of a configuration of a production environment. So in essence, every client saw a completely different system. Now, if you're talking about stuff like this, think about your Facebook feed. If you look on your Facebook, it's not the same as the Facebook feed of the person next to you. You're going to see something that's different. Your feed has different data. You might have different features. Maybe you're in an experiment. Maybe you're getting to the servers in Europe, and your friend is on VPN, is getting to the servers in the US. You're getting a different experience. You're talking to different versions of code. You're talking to different services, different software. And you're seeing different data. And in this situation, it's not meaningful to talk about a single production environment because every client sees his own universe, which is sometimes very different from the universe of other clients. Nowadays, it's more meaningful to talk about production environments plural, because every transaction, every client that talks to the system sees a different environment that is unique. It's impossible to recreate in staging or in some kind of laboratory and so on. It's, in essence, a one-time environment just that goes away after a few seconds, and it's not repeatable. You cannot repeat it. This means that we have lost the ability to try to reproduce bugs in the lab, because there really is no way to reproduce that environment in the lab. You're not going to have the same servers, you're not going to have the same configuration. Remember, it's an environment that changes every few seconds. There is no way to capture the exact state of that environment. So we have to think about this in a radically different way. Now, going back to our system, the next thing that happened that was very interesting is that we started deploying into containers, and it was on a fleet of servers. We no longer cared which service is running on which server, and we started virtualizing the network. So anyone using service mesh here? A few people, yeah. And if you're not using the service mesh, are you using VPC? Everyone is using VPC, come on, right? So the network is virtual at this point, so you don't even see it that much, which is interesting, because for some reason people still configure IP addresses and subnets, but I don't know, whatever. And the next thing that happened is that we stopped deploying on servers and we started using SaaS to deploy our code. So I'm using Fargate, for example. A lot of other people are using EKS, GKE, and so on. We no longer manage our own clusters. I just push an API call to Amazon, and they run my container on a server. I don't know even where that server is. I don't have a cluster per se. So I basically have a cloud service that hosts my code. I have another cloud service that hosts my data. And then, now I have another service that hosts my database. So DynamoDB, think about DynamoDB, for example. Nowadays, there's really no reason to install MySQL or Postgres or anything like that. If you want a database, you just go and you bootstrap RDS or use DynamoDB, and everything is on a cloud, on basically a software as a service platform. So you don't even have a database in the sense that you used to have a few years ago. Now, DynamoDB is an interesting case because DynamoDB talks what protocol? HTTPS, the same protocol that your browser talks. And it's the same protocol that your microservices talk. And one other interesting fact about DynamoDB, it is inherently public. You could talk to DynamoDB from a browser, and a lot of people actually do, because there's no reason why not. It is a public service. So now you have this kind of symmetry where all the parts in this cloud, whether they are internal or external, can talk to the database and the services, and the external services and the internal services, and there's really no actual difference at this point. And the internal network kind of vanished at this point, because if I'm talking to external services and internal services, and the database is actually internal or it's external, because I could talk to it from the inside or the outside, and it doesn't matter anymore, what is the value of the firewall? Why is the firewall still there? What is it doing there? It doesn't mean anything, does it? I mean, all the network is virtualized anyway. If you're on VPC, VPC is a tunnel, is a network tunnel on top of a public network. Because the cloud, EC2, for example, is by design public, it's shared. So what's the difference between VPC and, let's say, SSL over the public internet? And from a technical perspective, there is none. So it's very interesting because we have now this symmetry where everything is just a bunch of clouds talking to each other, might have code, they might have data inside of them, and they talk to each other using webhooks or HTTP calls or whatever. And we could just get rid of the firewall, and I suspect that in a few years we will. No one needs it really. But now we have this weird system that we cannot manage in the ways that we used to, because it's completely different. The word host, for example, has lost its meaning. If you're still using monitoring tools from the old days, monitoring tools used to divide metrics by host. Well, the hosts. What am I going to do with a metric that is attached to a host? It's meaningless. So we need to start thinking about this in a different way. First of all, the cloud is inherently public. Talking about private networks and stuff like that in a cloud doesn't make any sense. What we should be talking about is permissions. Does someone have permission to access this service? And this is one of the reasons why we see a lot of breaches in the cloud, because we still haven't adjusted to this mentality where what we have to defend is not IP addresses, but credentials. This is the system as it looks today. No firewalls, just a bunch of clouds talking to each other. And if you think about it this way, one of your major vulnerabilities is cloud services. For example, if you put data on S3, it's accessible from everywhere if I have the right credentials. If I put data inside of VPC, it's accessible from everywhere. How do I know it's accessible from everywhere? Because if I have the right credentials, I can actually put a gateway into your VPC. So again, it all boils down to credentials. A lot of the breaches that happen because someone steals something from GitHub. Your code is on GitHub. And maybe your credentials as well. Or maybe it's on the Terraform cloud or a bunch of the other clouds that you might be using. So what we got is a complex dynamic system hosted in an uncontrollable dynamic environment. How are we going to manage that? Good question. Enter the age of germs. So why am I talking about germs? Germs have a nice property. They survive in hostile environments. We find germs in the bottom of the ocean where there's no sunlight, almost nothing to eat, and somehow they survive there. They found a source of energy, they found something they could digest, and they survived. They multiply and they grow, and they just live there. We find germs in places we couldn't even dream of. And I think that we can learn a lot from biology about patterns in IT that we can use to build better systems. So a complex adaptive system is a system in which perfect understanding of the individual parts does not automatically convey a perfect understanding of the whole system behavior. And this is very important, this definition. Because we still have this mentality, this idea in our head that we should be able to understand and analyze all the parts of the system. We still think about, what is the configuration of all the servers? How are they configured? Are they configured the same? That's no longer meaningful, because this is a complex adaptive system, and a perfect understanding of all the individual parts does not automatically convey a perfect understanding of the whole system behavior. So yeah, you could know what is the configuration of each particular server and each particular service and what data you have, and it's still not going to lead you to an understanding of the whole system. So we have to give up on that and find different ways to cope. And biological systems give us a lot of good ideas. Biological systems, for example, germs, are composed of semi-autonomous cooperating cells, just like microservices. They are self-organizing, which is something very different from the way we build systems today. They are adaptive. They can recover from failures without an operator intervening, which is, again, very different from what we do today. They are also dynamic, and they have constant birth and death cycle. So nowadays, we retire servers, when they fail, and we replace them with new servers. But actually, one of the patterns that I introduced a few years ago when I was starting to work on cloud servers is we had a bot that automatically killed machines when they got too old, on purpose. Why? Because it was the easiest way to make sure that you didn't have servers with stale configuration that was too far from everyone else, and maybe had too little disk space and other problems that we didn't want to deal with. So we just killed them and replaced them constantly with new servers being reborn. It has innate variation. You cannot have a fleet of servers that is configured the same. It's just not going to happen. There's no way to do that. So instead, we need to accept that there's going to be innate variation. Instead, use constraints to make sure the system works despite this variation. And in fact, this variation leads to resilience. In the old days, we used to buy different types of hardware, because if you had a bug in one type of hardware, odds are all of your hardware is going to fail at the same time. So on purpose, we introduced variations to our system, and this is something that needs to be done again. And biological systems have the property of surviving in an uncontrollable and sometimes hostile environment. Newsflash, the cloud is a hostile environment. We need to learn how to make our systems survive in that environment as well. So how is that the design going to look? So on the right, we have a classical system where you have a single path of data or transactions through a system. And you know in advance, you planned in advance, and you can trace that path through the system. And this is something that's not very resilient by design. Why? Because in a single path, if one of those parts, if one of those connections, for some reason, does not work, you're not going to have a successful transaction. On the other side, you have the types of systems that we have today, where you have asynchronous connections, maybe multiple ones, maybe dispatch multiple requests, and you don't actually know which of the agents or which of the servers actually took care of that transaction. But it doesn't matter, because the only thing that matters is that you have some path through the system. And if you have multiple paths for success, then statistically speaking, the chances of completing that computation or transaction are much, much higher. And this is the type of systems that we should be designing. But how are we going to design this? So first of all, we need to understand that we need a large number of redundant agents, just like germs, which are similar but not identical. They would have variation. They would have short lifespan. They would be autonomous. And they would have convergent behavior. And instead of imposition, which is the way that we program today, what we need is a synchronous cooperation. I'm not going to talk about this too much, but if you're interested in that, this guy, Marc Borges, very smart guy, has been working on this for 20 years. And he published a paper called Computer Immunology in 1998, which brought those ideas, and actually he wrote some software, CF Engine, if anyone knows it, that took those ideas and actually put them in large scale on infrastructure management. He published a lot of books about promise theory, and which is basically the theory behind all of the stuff that I talked about, and how to build this new generation of systems that can actually survive in this world. So I highly recommend that you go and look up his books and read it. Really, really good. So just to sum up, the new challenges that we have on those systems. First of all, observing or observability. It's not about monitoring anymore, because everything is dynamic and it's an information-rich network. We have much more data. We cannot summarize it in static patterns like we used to. We cannot decide upfront what is an alert, what is failure. Failure doesn't even mean what it used to mean. It's something completely different now. We need to find how to manage semi-autonomous components. And if they're semi-autonomous, we cannot manage them in the sense that we used to, because you cannot give them commands. They're autonomous. How do you understand a very large assemble of loosely coupled, self-organizing parts? It's hard. You get this diagram that of millions of agents talking to each other. Just too hard to understand without tools that we don't have yet. And how do you control a system that is non-linear and chaotic? How do you do security in an environment that is public and hostile? And of course, how do you get resilience of the entire system when all the parts, just combine and fall apart all the time? So thank you very much. If you're interested, come talk to me after.